Good morning. Thank you for the introduction, and thanks for the invitation to give this talk. The lecture is about spin optics, spin symmetry breaking in nanostructures, and I am from Nano-Optics Laboratory, Technion. My colleagues are part of my group members, Dr. Vladimir Kleiner, Nir Shitrit, Nir Dan, Avi, Yuri, Kobi, Igor, Itai, and Sergei. We know that the spin is a type of intrinsic angular momentum of particles, intrinsic degree of freedom, and in general, isotropic and homogeneous systems are spin degenerated. If we would like to manipulate a physical system by use of the spin as a degree of freedom, we must remove the spin degeneracy. It is possible to remove it in the energy domain, Zeeman effect, or in the momentum domain, which is a Rashba effect. There are many spin-based effects in physics, like in Zeeman effect, Stern-Gerlach, in solid state is a spinol effect, and Magnus in fluidics. In addition to charge, electrons possess intrinsic angular momentum, which is the spin, and in 1971, Diakonov and Pearl published a very important paper about a spinol effect, applying electric field upon a semiconductor, results in a spin current in the transverse direction, which is a spin-dependent momentum shift or spin-dependent deflection of the spin-polarized electrons. Kato et al. Observed it experimentally upon a gallium arsenide substrate. So the spinol effect provides a method of separating electron with spin up and down. The spinol effect is attributed to the spin-orbit interaction of electrons, or the spatial trajectory of moving electrons is affected by their intrinsic angular momentum. Another very important effect is the Rashba effect, which is the signature of structural inversion asymmetry present in quantum wells. Forming inversion asymmetry quantum wells results in a gradient of potential in the z direction. We can write the Schrödinger equation for the electrons, or the Rashba effect, by using the corrected Hamiltonian term proportional to the spin operator and to the gradient of potential. The solution for this equation is a spin-dependent splitting of the electron dispersion, and we can write the spin-dependent momentum shift, delta K, proportional to the spin and to the gradient of potential. Ishizaka et al. Published an important paper by calculating and observing a spin split dispersion for electron for this Rashba effect. So, spintronics, which is a new emerging area of technology, exploiting the spin-orbit interaction effects like a Rashba effect or a spin-all effect, and in which both the spin and charge of electron are manipulated to create a new type of microelectronic devices. In optics, we define intrinsic and extrinsic momentum. Intrinsic momentum is a spin angular momentum, spin up associated with a right circular polarized light, and spin down with a left one. Extrinsic momentum is a linear momentum or orbital angular momentum associated with a spiral phase, where the orbital angular momentum per photon normalized by h bar is equal to the topological charge. Allen published an important paper about calculating the total optical angular momentum in the paraxial regime, which is equal to the intrinsic angular momentum, the spin, plus the orbital angular momentum, which is the topological charge. So in optics, it is possible to observe a symmetry breaking and to obtain spin-orbit interaction to allow spin angular momentum to flow to orbital and or a linear momentum. The spin of photons may provide an additional degree of freedom in nanoscale photonics, leading to a new branch in optics, which we call spinoptics. Recently, we observed the spinol effect or optical spin effect in a microscale system by launching a left and right circularly polarized laser beam into a glass cylinder, and we measured the emerging beam as a function of the incident spin state. We measured opposite deflection for the two spin states, and you can see here our measurement relative shift as a function of number of turns, and there is a very good agreement with our prediction. This is the spinol effect of light described by a Berry phase monopole in momentum space. Hasman and White published in Science a very important and nice paper about observation of non-adiabatic optical spinol effect based on weak measurement. They observed a spin-dependent deflection of the confined beam refracted from interface between air and glass. So the spin-dependent beam displacement and momentum shift are attributed to optical spin-orbit coupling between the intrinsic angular momentum and the trajectory. The optical spinol effect was observed in gradient index media in the microscale system. We would like to manipulate a nanoscale photonic system by use of the spin as degree of freedom, and of course we can't use the gradient index, but we can exploit geometric gradient in the nanoscale. In order to form geometric gradient, we utilize the localized surface plasmons configuration. We know that localized surface plasmons are non-propagating excitation of conduction electrons of metallic nanostructures coupled to the electromagnetic field. And in order to excite the localized surface plasmon configuration, we fabricated space variant nano antennas, as you can see here, results in a geometric gradient in the nanoscale. So I discussed a little bit about optical spinol effect or spin-orbit interaction. I would like to talk about spin-optics effect in plasmonic, in the nanoscale, plasmonic Aharonov bomb effect, to talk about spin-dependent plasmonic based on interfering of topological defects, and then to discuss about optical Rashba effect in a spontaneous emission, specifically for a thermal emission, and to finish with our recent investigation about spin-optical metamaterials. In order to observe the optical spinol effect or spin-orbit interaction, we utilize surface waves. Surface waves are evanescent waves. It can be surface plasmon polaritons, which are confined wave due to collective oscillations of the electron in metal, or surface phonon polaritons, which are the resonance collective lattice vibration in polar crystals. For the visible radiation, we utilized the surface plasma polariton, but for the mid-infrared radiation, for thermal emission, we utilized here the surface photon polaritons. Of course, the surface waves are evanescent waves, and in order to couple the evanescent wave into propagating wave, we must satisfy momentum matching, and it is possible to satisfy it by using periodic structure. First, we studied the optical spin-Hall effect in plasmonic chains. We studied two distinct plasmonic chains. A plasmonic chain consisting of isotropic nanoantennas along a curved path, and the second one, plasmonic chain, consisting of anisotropic nanoantennas with a space variant orientation direction along the path. We start here with anisotropic nanoantenna chain. We realize anisotropic nanoantenna as a rectangular nano apertures upon a very thin gold layer, and we fabricated a random nano aperture upon the very thin gold layer, and measured the transmission spectra for the scattering through this device. And as you can see, the scattering polarization follows the short axis of the nano antenna. Then we formed a coupled anisotropic nano antenna in a specific direction, and we observed here that the scattering, the polarization of the scattering wave follows the short axis of the nano antenna. Then we fabricated a plasmonic chains consisting of anisotropic nano antennas where theta is the local orientation of the nano antenna. We used here a local orientation of nano antenna which varies linearly as a function of x. We illuminated this chain with spin up and spin down and measured the k-space, the far field of the spin flip components. As you can see here, for illuminating with spin down, we measured a deflection for the spin flip component, but illuminating with spin up, we measured opposite deflection for the spin down. This is a spin-Hall effect. This is a spin-orbit interaction of light, and we can define here omega as a spatial rotation rate, which is a gradient of theta. So the spin-dependent momentum shift is proportional to the spatial rotation rate of our structure. I would like to talk a little bit about isotropic nanoantenna chain. We fabricated isotropic nanoantenna as an annular aperture upon a very thin gold layer, and we fabricated here a coupled isotropic nanoantenna chain onto a straight line, and we measured a longitudinal mode as well as a transverse mode. Then we fabricated a curved plasmonic chain consisting of the isotropic nano antenna, where the local orientation of the chain theta varies linearly in the x direction. We observed here the same spin-orbit interaction, the same spin-Hall effect as in our previous experiment, and here the spin-dependent momentum shift is proportional to the spatial rotation rate of the curved structure. We can understand it as analogy with the angular Doppler effect of rotating pi retarder. For example, illuminating a sigma state of light onto a rotating pi retarder results in a frequency shift proportional to omega t. Omega t is the rotational rate of the retarder in the time domain. In order to analyze especially rotating nanostructure, we can think about rotating reference frame attached to the anisotropic path. Then, instead of theta as a function of time, we can write theta as a function of the path, as a function of the xi. And instead of a Doppler in the frequency domain, we will have here a spin-dependent deflection or spin-dependent momentum shift delta k proportional to omega xi. Omega xi is a gradient of theta, which is the special rotation rate of the structure. Integrating it results in the Berry phase, which is a geometric phase proportional to the theta, to the orientation function of the structure. Of course, there is some difference between scattering effect and absorption or emission effect. The difference is a factor 2, as you can see here. We can understand it as a general, a geometric Pancharatnam Berry phase by traveling upon a Poincare sphere. It can be traveling upon another Bloch sphere. It results in a geometric phase, where the geometric phase is equal to the half of the solid angle of the traveling upon this sphere. And you can see here the absorption as well as the scattering mechanism, where the geometric phase is spin-dependent and proportional to theta. The Helmholtz equation in non-inertial reference frame rotating with a rate omega is presented here with the additional Coriolis term proportional to omega, where the eigenvectors for this equation are the spin states. We can write this equation as a generalized momentum, where the generalized momentum k is equal to the unperturbated k plus sigma omega. The dispersion solution for this case is a spin split dispersion, omega as a function of k plus sigma omega. Then we formed a closed plasmonic chains consisting of isotropic nanoantennas as well as anisotropic nanoantennas rotates m-fold, m times along the chain, and we measured the k-space, the far field of the spin flip component results in a dark spot. Dark spot is a signature for orbital angular momentum, is a signature for a spiral phase, and of course we can analyze it by taking xi as a path proportional to phi. Theta is the local orientation of the nano antenna, which is equal to m phi. So we can calculate the special rotation rate in this case and the spin-dependent momentum shift delta k proportional to 1 over r. Integrated it results in a spiral phase where the topological charge or the orbital angular momentum per photon is equal to 2m sigma. In order to measure this orbital angular momentum or the topological charge, we interfere a twin closed plasmonic chains, as you can see here. And of course, you can see here the fringes of the interference pattern, and there is a dislocations. The number of dislocations here, the force, is equal to the topological charge with a good agreement with our prediction. We also observe an optical spinol effect for the surface wave, for the plasmonic wave. In order to do that, we realized a Bragg grating with a defect or resonator inside upon a gold layer surrounding by a coupler to couple the incident beam, the propagating wave into a surface wave, and we measured the surface wave inside the defect, inside the resonator, by using near-field optical microscopy, and we measured both for spin up and for spin down a dark spot, which is a signature, in this case, for a orbital angular momentum of the surface wave. We calculated the phase of the surface wave to be a helical, to be a spiral phase with a opposite helicity for spin up and for spin down. So we can write the field, the surface wave, as a spiral phase, where the topological charge is equal to the incident spin states multiplied by a Bessel beam. We can understand it from conservation law. We know that invariance with respect to spatial rotation leads to conservation of the angular momentum. So the angular momentum of the incident beam must be equal to the total angular momentum of the surface wave, but the surface plasmon can have only extrinsic angular momentum, so the orbital angular momentum of the surface wave must be equal, in this case, to the intrinsic angular momentum of the propagating wave. We would like to present here our experiment to distinguish between the intensity of spin up and spin down. In order to do that, we added a spiral structure, introduced additional spin-independent dynamic phase. In this case, we realized L structure, which is equal to 1 lambda jump in this spiral phase, and we illuminated it with spin up and spin down. For spin up, we observed a dark spot, which is signature for orbital 2, and for spin down, we observed a bright spot, which is no orbital angular momentum of the surface wave. We utilize this effect in order to observe the spin-dependent transmission through an annular nano aperture. We realize a nano-annular aperture upon a gold surrounding by a spiral structure. We illuminated it with spin up and spin down and measured the transmission through an isolated nano aperture. And as you can see here, we measured an extraordinary enhanced transmission for spin down and low transmission for spin up. So we have here spin-dependent transmission. In order to demonstrate this effect, we realize a two-dimensional nano aperture with a right and left-ended spiral structure illuminating with a spin up results in a spin picture. Of course, for spin up, we have here inverse picture, and illuminating with spin up and with spin down, we observe, of course, a uniform intensity in this picture. We can understand it as the angular selection rule in a light surface plasmon scattering process. The total angular momentum of the incident beam is equal to the intrinsic plus extrinsic if we have. We couple it into the surface wave, so the total orbital angular momentum of the surface waves is equal to the angular momentum of the incident beam plus the angular momentum due to the spiral structure, which is L structure. Of course, we have here annular aperture, behaves as a plasmonic waveguide, and we can define a orbital angular momentum to the plasmonic mode, L guiding mode. In order to couple the surface wave into the plasmonic guiding mode with high efficiency, we must satisfy the angular momentum selection rule, which is the L surface L of a surface mode must be equal to the L of the guided mode, and we have the angular momentum selection rule. In our case, we realize annular aperture allowed excitation only for L guided mode plus minus 1. We realize L structure, spiral phase, which is equal to 2. So we have an angular momentum selection rule. The angular momentum selection rule in this case is satisfied only for a sigma minus, and there is a very good agreement with our experiment. We also observed an optical spinel effect for a plasmonic lens. We realized a plasmonic lens, a coupler surrounding by a Bragg grating, and we illuminate it with spin up and spin down and measure by using a near-field optical microscopy the location of the focal spot of the surface wave. As you can see here, there is a spin-dependent deflection of the focal spot with a very good agreement with our prediction. Of course, by illuminating both with spin up and spin down, we observed a dark spot. Actually, we can see it as an optical-like Stern-Gerlach experiment. I would like to talk about our plasmonic Aharonov bomb. We address ourselves what will be the scattering effect from a topological defect. We realize topological defect as an annular aperture, and in order to measure the scattering, we interfere it with a plane wave of the surface wave excited from a very narrow nano slit. We measure the interference pattern by using the near-field optical microscopy, and as you can see, we obtain a phase dislocation, but a phase dislocation in opposite size between spin up and spin down. We can define here a strange of phase dislocation alpha, which is the number of wave crest ending on the dislocation, where alpha is equal to sigma, which is the orbital angular momentum per photon. So the scattering results in a spin-dependent plasmonic vortex in this case. We can see the analogy with Aharonov bomb effect. In Aharonov bomb, we have vectorial potential A proportional to 1 over R. In our case, we have a rotational ray proportional to 1 over R. This is a Schrödinger equation for Aharonov bomb with the corrected term, and this is our Helmholtz equation with the Coriolis term. The solution here is a momentum shift proportional to A. In our case, this is a spin-dependent momentum shift proportional to omega, and the phase dislocation strange can be calculated by a closed integral. In Aharonov bomb, it's equal to alpha. Alpha is a flux parameter. In this case, in our case, the phase dislocation is a sigma, the incident spin. So the spin in our case behaves as a flux parameter in Aharonov bomb effect. So we studied the scattering from a topological defect behaves as a plasmonic vortex source. We would like to exploit it for spin-dependent plasmonics based on interfering of topological defects where the point spread function in our new system is a spin orbit point spread function, which is proportional to Hankel function and a spiral phase where the topological charm is a sigma. We realized a plasmonic chain consisting of topological defects, and we measure the near field to be a dark spot, and there is a very good agreement with our calculation based on interference of topological defects. We calculated a spiral phase with opposite helicity for spin up, for spin down. Then we realized a plasmonic chain consisting of a topological defect, and we measure here a spin-dependent deflection of the plasmonic focal location proportional to the 1 over the wave number of the surface wave. I would like to talk about a geometric effect in a thermal emission. Professor Graffet and his group observed coherent thermal emission by coupling a thermal excited surface wave into a radiative wave, and we too realized a linear grating upon a silicon carbide. Silicon carbide support surface for non-polariton in the mid-infrared for a thermal emission, and we observed a very narrow spectral peak for the thermal radiation in the mid-infrared in a very narrow observation angle. Then we ask ourselves, what will be the geometric effect for especially rotating nanostructure, where omega is a spatial rotation rate? In order to study it, we form inversion asymmetry lattice. We know for a basic physical rule that if we have inversion asymmetry lattice, the dispersion must be spin-dependent dispersion. In order to study it, we realized inversion asymmetry lattice upon a silicon carbide, comprising of thermal nano antennas where the orientation varies linearly as a function of x. In order to study it, we characterized first the isolated thermal nano antenna. As you can see here, we measured the spectrum for a normal direction, and we observed two localized modes where the polarization of the modes follows the short axis of this nano antenna. There is a very good agreement with our calculation based on a modified long wavelength approximation theory. Then we realized a two-dimensional nano or thermal antenna array in a uniform orientation, and we measure, in addition to the local mode, a very narrow collective mode where the polarization of the collective mode follows the short axis of the nano antenna. Then we measure the wall dispersion relation for the thermal emission, which is omega, the frequency as a function of k, as a function of the signs of the observation angle in the x direction, and we obtain a slow mode as well as a fast mode, and there is a very good agreement with the momentum matching condition using the reciprocal lattice G and the wave number of the surface for non-polariton in this spectrum. Then we fabricated the inversion asymmetry lattice, as you can see here, and we measured the thermal dispersion relation. And as you can see here, we measured a splitting of the slow mode. In order to understand it, we measured the spectral intensity for a specific observation angle passed through a circular polarized filters, and we observed one peak for sigma minus and the second one for sigma up. So there is a spin-dependent effect for the thermal emission, for spontaneous emission, and there is a very good agreement with our reflection measurement. But here, instead of emission, we have a spin-dependent dips, a spin-dependent absorption. Then we measured the spin-polarized dispersion of this inversion asymmetry lattice, which is measurement of the third Stokes parameter, and we observe spin split dispersion of the slow mode, spin up and spin down, and there is a spin-dependent momentum shift, delta K. In order to understand this delta K, we realized a different inversion asymmetry lattices with different rotational rates, and we measured this spin-dependent momentum shift to be equal to a sigma omega, where we can conclude that we have here a spin-dependent dispersion omega with a good agreement with our prediction. It's very nice to see it as an analogy with a Rashba effect in electronics. In Rashba, there is a gradient of potential. Here we have geometric gradient. We can write the Schrödinger for Rashba equation with the corrected Hamiltonian term. And here we have our Helmholtz equation. The solution here is a spin-dependent momentum shift proportional to gradient of potential. In our case, it's spin-dependent momentum shift proportional to omega. You can see here the observation, experimental observation, which was done by Zaka, spin up and spin down. And this is our spin split dispersion. So we named our effect, or this effect, as the optical Rashba effect. I would like to discuss a little bit about our recent investigation, which we call spin optical metamaterials. Our inspiration came from antiferromagnetic Kagome lattices. We know that there is a geometric frustration, and there are several magnetic moments configuration, such as Q0, which is inversion symmetry lattice, or a square root 3, which is inversion asymmetry lattice. Instead of using magnetic moments configuration or spin configuration, we used here a localized Mon configuration excited by a nano antenna in a space variant orientation direction. For the inversion symmetry material, we observe spin-independent deflection. However, for the inversion asymmetry Kagome lattice, we observe spin-dependent deflection, and you can see here omega as a function of azimuthal angle, and there is very good agreement with a basic direction with inversion symmetry violation. So we know that from physics, if a parity transformation R2 minus R doesn't preserve the local crystal structure, then we will have a spin-dependent dispersion or spin split dispersion. We calculated the surface waves, the Bloch modes, by using a vectorial calculation, and you can see here that our structure consisting of 3 geometric meta-molecules, where the meta-molecules excited a surface plasmon vortices with different vorticities. So there is a relation between the spin symmetry breaking and the surface waves orbital angular momentum gradient results in the geometric Berry phase, the spin-dependent geometric phase. Currently, we also investigated a spin optic metamaterial for the nanoscale. You can see here, this is the inversion symmetry structure, and this is the inversion asymmetry structure. I would like to conclude that utilizing the spin-orbit interaction mechanism in optical devices may lead to development of a promising new area of research, spin optics, and we hope that we will be able to control light in all optical nanometer scale devices in ways that were impossible before. And we believe that there will be application, spin-based nano-photonic device, light manipulation by spin optical metastructure, nanomotors for nanoparticles, and we have a lot of research about DNA rotation, and of course, it can be a research platform for spin-based effect in physics, in solid state, and in material science. I would like to finish with Anderson saying that physics is a study of symmetry. Thank you.